about what are the general sort of areas that we as a community need to make progress on in order to move forward and actually one day have successful quantum computing. Okay, so an important area in sort of developing the quantum algorithms for quantum computing is to get state preparation right. So state preparation says the following: if you want to run a quantum computer, you've got to like set up some input on it. You've got to get some initial state into the device. And it turns out that strangely enough, that is the bottleneck in a lot of cases. If I want to simulate some quantum many-body simulation, if I want to run some differential equations on some grid, if I want to try to do some sort of quantum machine learning, at the end of the day, the thing that I need to get right is I need a state on my computer that sort of sets up the initial conditions. And so we spend a lot of time sort of developing techniques to improve state preparation. So for example, we have projects on asking ourselves, how can we use classical computers? How can we like sit on some high performance computing device and try to figure out how to intelligently and smartly optimize circuits that generate states for us efficiently. In fact, one of my main stories today will be sort of a shortcut to generate states efficiently. We've worked developing new tensor network algorithms that look at state preparation on neutral atom devices and ask, look, is state preparation on these devices robust to various sort of errors that are natural on the devices? So once you start getting state preparation down, what's the next step? Well, the next step is that you really got to push the algorithmic kernel forward. So this is sort of what we all sort of think of when we think about algorithms. We want to, at the end of the day, do something on our quantum computer. So for example, something that's very common to do or very common to want to do is to get the ground state of some quantum system. You might think, oh, it's a quantum computer because the word quantum on it should be able to do that easily. In fact, that's not the case. The algorithms to get ground state are fine, but not that great. In fact, there's some lower bounds that tell us that for a generic Hamiltonian, you can't really do a very good job to get a ground state. Okay, but we don't actually care about generic Hamiltonians. So we've spent some amount of time thinking, look, suppose you had a special Hamiltonian, a Hamiltonian that we might care about or that has some special properties. So for example, we did some work here on nearly frustration-free Hamiltonians. Could you use quantum algorithm techniques, something like qubitization or quantum phase estimation, to more efficiently get ground states? Okay, and the short answer there is yes. We've also spent a lot of time developing quantum classical hybrid algorithms. What's a quantum classical hybrid algorithm? It's an algorithm where your quantum computer runs for a while, gives your classical computer some information, your classical computer churns for a long time, hands something back to the quantum computer, and it goes back and forth. Actually, that's not what most of these look like. Most of these, the classical computer does almost no work, but at least this one, the classical computer has to sweat. And here we developed a technique to do sort of efficient variational imaginary time evolution. This is useful if you want to compute finite temperature properties of quantum many-body systems. It's useful if you want to compute ground states. Okay, and then once you've got sort of algorithmic kernels down, what's the next step? Well, quantum computers are expensive to run, right? There aren't very many of them, on high demand. Whatever you get out of your quantum computer, you really want to use as fruitfully as possible. And so this post-processing step is often ignored. This is actually something that we spent a long time thinking about. So if I come to you, here we go. And I say, okay, here's my quantum computer output. I don't want to just get a number. What I want to do is sort of use it fruitfully. So we spent some time thinking about, can we use sort of machine learning to take the energies that we're getting out of a quantum computer, maybe the energies from some ground state, and parameterize some potential, some molecular potential. So you could do molecular dynamics on a classical computer. Why should you use your quantum computer to get out a bunch of energies? For here, we built on some ideas of classical shadows. This is one of my favorite results. Someone takes your quantum computer and runs it on some random inputs and outputs. Spends a couple hours running it on random inputs and outputs, and stores the results of those random inputs and outputs. And then tomorrow or next week, you can take those results and you can, on your classical computer, rerun your quantum computer on an input you care about and an output you care about. And the promise is that gives you the same answer in expectation. Okay, so this is a little bit magical. So we pioneered sort of this approach of process shadow tomography. It's not as magical as it sounds, because my promise is only that in expectation you get the right answer. But it could be a really noisy answer. For some inputs and outputs, it's really good. For some inputs and outputs, it's really good. But I still think it's kind of crazy obsessive. What that means is that your classical computer gets to pretend it's the quantum computer you ran. You don't even need to know what was run in that quantum computer. You just need access to the random inputs and outputs that you did. And in expectation, on average, it just does the same thing. I think that's cool. And then finally, beyond all of sort of the algorithmic pieces and the minor detail of building it, you need to get error correction. So a major problem with quantum computers is that they're extremely error prone. And so what does that look like? Well, really, you're spending about 99% of your time on a quantum computer doing nothing but essentially correcting the errors. And so we've done various things in error correction, some error mitigation on IBM devices. Here, we use diffusion models, which is sort of a modern machine learning technique, to take the syndrome, the measurements that are coming from a quantum computer, and decode what those errors are, particularly in quantum LDPC code, to kind of efficiently and accurately look at the syndrome, say, oh, this is the error you made, this is the thing you have to go fix. And this is working well, partially because of modern machine learning, but partially because it's heavily relying on fast classical devices such as GPUs. Okay, so look, I've given you sort of a bunch of vignettes, a bunch of things that we have to do to move quantum computation forward. And something you might notice, kind of a common theme, is that, get rid of this, this thing here. There we go. Quantum computers are more powerful than classical computers, but let me 80% of the vignettes I just told you about, classical computers have an important role to play. They're classical quantum hybrid algorithms, they're GPUs to do the error correction. There's classical computers that are storing, post-processing the output in a highly non-trivial way. This isn't just sort of doing something non-trivial. And so it is worth asking about the interplay between quantum computers and classical computers. And that's going to be the core story today. Now the buttons no longer work. Okay, and it's worth asking, really, for both kind of a practical reason and a fundamental reason. The practical reason is the following: quantum computers are terrible. Now that's a little bit contradictory to what I just told you, that quantum computers are amazing and going to solve intractable problems, but it happens to be that both of these things are simultaneously. And the things that quantum computers are good at, they're going to scale exponentially faster than classical computers. And so on those things, because you're winning by 2 to the 10,000, it's worth it. But on everything else, quantum computers are terrible. They're going to run at a clock speed that's natively much slower than your MacBook. And then once I do quantum error correction on top of it, they're going to really, really run at a clock speed that's natively much slower than your MacBook. I'm spending like 99.9% of my time doing quantum error correction on the quantum computer, not actually calculating. Anything that you can avoid doing on a quantum computer, you should avoid. And so, like, for practical engineering reasons, we should go ahead and try to offload anything onto the classical computer that we can do. Okay, but beyond that, I think that answering the question, what is the dividing line between what quantum computers can do and what classical computers can do, is like a deeply fundamental question. One of the most deep fundamental questions sort of of our universe. Really, it speaks to sort of the question of what is possible efficiently in computing. Right? What is the power of quantum computing? Where is it coming from? Is it entanglement? Is it magic? Is it something else? What is it that is giving us the ability to sort of beat out what for a long time people thought was the case, which is that all computing devices, whether it's MacBook or cellular automata or billiard balls or vacuum tubes or Babbage's engine, were more or less just as fast as each other, and it's just a question of the clock speed. So I think both of these things can simultaneously be true. And so I'm going to tell you 2 stories today, which actually have, or at least 2 core stories, which actually have different different morals in some sense. One is going to be about, can we use measurement plus adaptive feedback? I'll tell you what that is in a moment, for state preparation. For the state preparation, it's important thing to be able to do to essentially offload some quantum work out to classical work. And then the second story I'll tell you is, are there sort of large classes of quantum circuits, highly entangled, highly magic quantum circuits, so we can go ahead and simulate these. I should say, if people have questions, by all means, interrupt me. How's that? All right, so here's story one and goal one. Our goal here is we'd like the quantum computer to do some of the work. What part of the work? Well, kind of our intuition is that quantum computers, like what makes them powerful is that they can entangle things, right? They can build up large entanglement. So our hope is that the quantum computers can do that part of the work, and then somehow we can offload for some of the state preparation, some of the rest of its cost. Okay, and so we're talking about state preparation. So what does state preparation mean? It means I have some state psi, and my goal is to like draw a quantum circuit. I'm going to run on my quantum computer to build up. And so we might ask the question, why can't I do this fast? There's some circuit that builds some state psi. Well, why can't my circuit be any quicker? What's preventing me from doing that? And one answer to that question might be that there's some entanglement speed. And in some sense, to build up this state, the state has some entanglement. And when I have a quantum circuit, there's only so fast that I can build up the entanglement. Local gates, entanglement only builds up a certain speed. So for some states, the answer to my question might be, I can't make this any faster because there's some speed limit, there's some amount of time, there's some circuit depth that I need to build the requisite amount of entanglement to store that. But it seems that for many, many states, that is in fact not the case. So this is true if I take a random state from the Hilbert space. It's true of many, many other states. If you look at the entanglement versus time or circuit depth, we reached the requisite amount of entanglement for that state to exist way, way before we managed to build the state. And here's some numerical data. So suppose you want to prepare the ground state of the transverse field Ising model at the critical points. It's a standard condensed matter model. The amount of entanglement is logarithmic, sort of by depth 5 or 8 or something. You've successfully built your different system sizes, the necessary, not depth 5 or 8, depth 2 or 3, you've successfully built up the amount of entanglement you need to make that state. But if you just ask how long does it need to take the state, this is just actual numerical data, it actually takes much larger depth to pull off building the state. So like here's a concrete example where my quantum computer has built up the needed entanglement, but somehow I still need to like churn for a while to get the state. We can ask a similar thing about subset states. Subset states are linear combinations of a small number of binary numbers. 1, 0, 1, 1 plus 0, 0, 1, 1, 1 plus 0, 0, 0, 0, 0. Okay, these are very popular quantum cryptography. Macron works with these a lot. And these are very low entanglement. Linear superposition of a small number of things, the entanglement isn't very high. And we can ask, look, if I build up the requisite needed amount of entanglement, what is the probability that that is sufficient to build the state? There are many such subset states, and all this graph tells you is that as the subset states get large, as they're 10 qubits, the probability that I can successfully build that state once I've got the requisite amount of entanglement is like 1%. In other words, like here are all these states, you just can't build them in the depth that you need to build up the entanglement. And so what our hope is here is that we can go ahead and we can say, look, at this point, the quantum circuit has built up enough entanglement. Let's go ahead and somehow, at least in some cases, replace the rest of this with a classical case.
The question on the back is,
yes.
We talk about a probability of creating the entangled state. I'm thinking of unitary gates, and so I feel like if I do the right unitary gate, the probability is 100%.
Yeah, okay, good. So
Some kind of a measurement.
no. I just said this in a confusing way. There are millions of these states. Some fraction of them, the depth required to build the entanglement of the state or the state. But for the large majority of them, that's what this probability is measuring. It's just saying, look at all the subset states, or sampled over many of the subset states. It just asks, for this one, can you build it in the time required to build the entanglement? Can you do it for this one? Can you do it for this one? And the upshot here is that for most of them, you need much longer circuits than the entanglement can suggest. Great, thanks for the question.
Actually, kind of related to that problem, it's hard to build the states. But if you were to have them, it's probably equally hard to know whether they are difficult. Right?
That is true, and that is something that Mercant is working on very heavily in sort of cryptography. True, but not necessarily an important part of the story. Great, other questions? Yes.
When you say that you need some time to build the state, do you mean some kind of theoretical required time, or do you mean with this particular algorithm?
I'm saying that as best we can tell, and there's some both numerical evidence and sort of analytic evidence to that, there's a theoretical sort of bound. How long you can build this thing. Other questions? Yes.
The slope of the line is plot at like sensitive dependence on gate set of hardware, or is it totally unrelated?
Not in any deep way.
Okay.
There may be some dependence, but not in any deep way. Great, other questions? Okay, so what we would like to do, kind of morally speaking, is we like to like build up enough entanglement, and that's what quantum computers are good at, right? Quantum thing. And then we like to replace like the rest of the stuff with a classical computer. Like that doesn't like make a lot of sense. Like, okay, there's my classical computer. And like, I don't know, classical computers neither eat nor give back quantum states. Like, stick it in the floppy drive or something. That doesn't help you. So what do I even mean when I say these words? I'd like to replace some of the effort with a classical computer. Well, one thing I could imagine is the following. I want some critical transverse model state. It's on 4 qubits. So what I can imagine doing is building up some state on more than 4 qubits, 6 qubits, 8 qubits, whatever, say 6 qubits. And then I measure 2 of these qubits. Okay. Now I have a 4 qubit state because they're destroyed, they're measured. But I can inform my classical computer what those measurements are. So this time, stochastically, I got a 0, 1. The classical computer can churn on whatever processor this is. And it can say, oh, well, to build the rest of the state, you should go ahead and use these gates. And that might depend. If it got 0, 0 instead, then the classical computer might tell you something different. So this is called measurement plus adaptive feedback. This was probably the first paper that showed that you can use this technique often to accelerate the building of various states. Okay, so here, what is the goal? The goal is that instead of doing this long quantum circuit that was living on the previous page, not that page, that instead of all of that goes away, maybe we have to change these initial quantum gates as well, and you just replace it with this process. And so you could ask, like, is this possible? Is it generic? Is it just fine-tuned? Maybe we can only do it for 1 or 2 things. So what we did is we built an algorithm to find these states. You give that classical algorithm a state, and it churns and it finds it. This is a pain in the neck. You might want to do something like gradient descent, and that failed miserably. So you're going to do some like fancy environment tensor network things, but whatever. We have this algorithm. And what it does is you give it a state and it searches. Okay. And so now we can ask the question, as we like hand it various states, do we do better? Okay, and the way we like to ask this question is we're going to fix some depth. The unitary circuit gets to run depth 7. And then we're going to fix the same depth where we're going to allow it to do measurement plus depth. And then we're going to ask how close did it get? So here are 3 states: the transverse field Ising model, critical state, a random matrix product state, and a subset state. These are all judiciously chosen to have entanglement that is much smaller in general than the depth needed to take it, to build it. And the orange is, so this is a log plot, this is infidelity, smaller is better, like orders of magnitude, right? The orange is the quality you get when you use measurement plus adaptive feedback, and the purple is the quality you get when you use a standard unitary matrix. And in the transverse spherolicing model, this is 18 qubits, you get an order of magnitude improvement. In random MPS, you get an order of magnitude improvement. This is 10 qubits. In the subset states, you get like 8 orders of magnitude improvement or something. This is again 10 qubits. So here are a bunch of examples where you win by using measurement plus adaptive feedback.
What is the circuit depth for the what is the depth of the adaptive circuit? So here SWIFT is just optimizing SWIFT, I guess.
Sweeps is just optimization sweeps, yeah.
So then like what is the depth of the actual adaptive circuit?
The depth of the circuit, I don't remember off the top of my head. I could look at it, but it's tuned to be enough to build the advanced. I mean, yeah, I don't remember off the top of my head what these are all different depths, but they're fixed. It's the same depth for both the measurement plus adaptive feedback.
So adaptive part is just on site or two sites.
Say that.
So adaptive.
The adaptive part in this particular case is just on site. So it's not adding any more entanglement. You can of course do other things. So we looked at algorithms to do other things. But for this particular calculation, it's just on site. Great, other questions? Okay, so that's all well and good. What that tells us is we have an algorithm, and in lots of cases it finds, so in very generic cases, the measurement plus adaptive feedback helps you. But the problem with an algorithm is sometimes it's like hard to understand what it's doing, right? It's just doing some fancy optimization. The advantage is that it tells you it works, kind of in generic sense. But it would be nice to be able to sit back and kind of analytically have some understanding of what's going on. So here we're going to do the opposite. Here we're going to think hard. So this is work where we have a student Abed and co-for software Kevin. And instead of writing down an algorithm, we're going to talk about a class of many states, but a little bit pinchy states, where we can analytically understand how you can use measurement plus adaptive feedback to significantly accelerate their state progression. Okay. So here's the class of states, and then I'm gonna like walk you through a lot of the like argument and proof and like what's going on. And I'm going to do that with essentially no equations. I'm just going to draw like fancy concerned network diagrams or on the screen as it turns out. Okay, the state is the following. It's a class of matrix product states. If you don't know what a matrix product state is, that's okay. These matrix product states have a special property. They have a global symmetry, global on-site symmetry. And that global on-site symmetry has a special property. There is an irreducible m-dimensional representation of that symmetry. Group theory there. And if you have such a irreducible representation of that symmetry, then there exists a measurement plus adaptive feedback circuit that constructs this MPS in constant time. Otherwise, you need linear time. So that's a huge, huge speed up. Although it is sort of like a niche process. Okay, so what I'd like to do for the next 10 minutes is to walk you through some intuition for like where this is coming from and how this is. So let me pause for a second and ask if there are any questions.
Constant time does not depend on the representation.
It might depend on the representation. It doesn't depend on how long it is. If I want to do 100 qubits of this MPS and 1,000 qubits of this MPS, normally it would take sort of time 100 or certain depth 100 or certain depth 1,000. Here, this is independent, constant time. This is a huge, huge win. Okay, so what is a quantum state? Well, it's just like some black box, it's even black there. It needs some configuration, up, down, or some electron negations. It gives you a number. Yes, Felix.
Sorry, to the previous slide, I'm a little confused how you use global here, because you also said it's an on-site symmetry. So
it's an on-site symmetry, like SU2 symmetric or Z2 cross Z2 or Z2. It's the symmetry that this MPS has is a symmetry where it's on every site. So if I apply the symmetry on every site, I get this increase.
So unless you're in some sort of fixed point, like you will not get irreducible, like n to be small. Usually the bond dimension will be larger than the irreducible representation.
Yeah, so there's a representation on site, which is tiny. And in addition, that group also has an m-dimensional representation.
Right, but like, for example, in the case of like Z2 or Z2, like, there is a limit on how large it can be for the reducible representation.
That's right. So in some cases, there's some bound on how big this should be, but you should make a distinction between this representation, which is a representation on the site, sort of a two-dimensional space, and whether or not there exists sort of a higher dimensional representation, M, that also exists for this.
For C2, that's a building group, so they're all one dimension.
Yeah,
So like a high dimensional array means that you have some kind of knowledge.
yeah, so but even for non-abelian, usually the exact MPS has it's not consisting of like only one particular irreducible representation, usually a direct sum of like multiple different irreducible representations, so I wonder whether this is going to work in such a generic situation.
It does when you have a product of some irreducible representations, but there's some details running around. This is a nifty class. It's one we kind of speak about the details of sort of where it does and doesn't work. Other questions? Okay, so what is a quantum state? Well, a quantum state just eats a configuration and spits out a number. What is a matrix product state? Well, it's a quantum state that eats a configuration and spits out a number. It's made of a bunch of 3 tensors. One of those specifies the index up or down, the spin system. And then the other 2 are these auxiliary bond degrees of freedom. Essentially, what this tells me is if I commit to up, this is a matrix. To get the number, I multiply the matrix for site 1 up, the down matrix for site 2, the down matrix for site 3, the up matrix for site 4, and the down matrix for site 5. That gives me a number. That is the number that this configuration is. This matrix size is called the bond dimension M, and its entanglement is proportional to the bond dimension. Okay, so now if I want to do like the canonical thing, and I'm like, I would like to take my matrix product state, and I would like to turn it into a quantum circuit. Not a measurement because adaptive feedback quantum circuit, but a boring one. What I should do is the following. This is a 3 tensor. It has alpha, beta, and I. And I'm just going to like no pi dot reshape. I'm just going to like make it a matrix by dragging the I over to this side. Now this is no longer a 3 tensor. It is now a matrix where one of the indexes is alpha I and the other index is beta. Okay. And now all I'm going to do is I'm going to promote this tensor, which is a matrix, could be rectangular, into a unitary matrix. And there are some details. I essentially have to pad it a little bit. It's not unitary because it might be rectangular. And so I'll add some like extra wires at the beginning that are 0, and extra wires at the end that are measurements. So that it is now a nice square unitary matrix. The experts in the room, these actually have to start as an isometry. So I should take my matrix product state and canonize it. So it's isometry. Okay, and so that is the canonical approach to turn a matrix product state into a quantum circuit. And then time goes this way, and everything is good because, like, on the left of all of these gates, I have zeros, and on the right, I have measurement or wires. At the end of the day, I get 5 sites, which is my 5-site MPS. That's the end of my quantum circuit. And now I'm holding on to qubits that represent these. And then, okay, I have to decompose these unitaries into standard gate sets. That's straightforward. The thing that you should take away is this takes linear time. Right? For every qubit, I need some gates. Okay, and now what I want to do is I'd like to go ahead and turn this into a constant constant. And so now we're just going to do like proof by diagram. This is the tensor network that I'm working with. And all I'm going to do is I'm going to like change like where things are drawn. And so here we have now drawn it in some different way. And it's still obviously the same tensor network as all that matters is topology, who's connected to whom. And again, I can turn all my tensors and make them unitaries. And now I'll just say time is this. Right? Except for there's a problem. This is not how time works. If I have time going this way, it better be that there are like wires up top that go to wires down below. I don't get to have wires that like do this squiggly thing that are going like forward and back. So what I need to do is I need to take my tensor network, which I've tried to promote to some unitary circuit. In fact, I've promoted a bunch of things to unitaries. And now what I need to do is go ahead and replace these things. Okay, I need to replace them with like some circuit up here. And I will now, this looks a little bit subtle because like who the freak knows what's like on these wires. But I will now use a very exotic property of wires, which is whatever is here is also there. And so what should we do? Well, what we should do is we should pick a state that has the property. If it's 0 over here, it's 0 over here. And it's 1 over here, it's 1 over here. And what is such a state? Well, that state's just an EPR, right? 0, 0 plus 1. Okay. So I should just replace this thing up here with an EPR pair. Maybe I need a generalized EPR pair, but it's some bond dimension. And I go ahead and I do that. And now I know this is looking better, except for I have to do something at the bottom as well. That's a little bit more subtle. It's a little bit more subtle because I don't get to put some unitary circuit above it. The wires are coming down. This is my direction of time. So I have to sort of do the opposite. I can't replace it with an EPR pair. I have to replace it with a measurement to the bell basis. And then I have to hope that I get to. And then if I do all that, I should declare success in some sense. I've now turned my tensor network into a quantum circuit. Time goes this way. That depth does not depend on how many qubits. Then unfortunately, but very importantly, in order for this to work, I have to get extremely lucky. And after I do the measurements, everybody has to be 0. Probability that happens is exponentially tiny. But if your goal is to produce a quantum state with an exponentially tiny probability, this will actually always work. For any MPS you want, essentially any state you want, you just have to get really, really lucky. Okay, that's a little bit dissatisfying. And if you don't get lucky, what happens? Well, you get a bunch of states with defects. This is what you wanted, A, and actually there's some other defects. So what can you do? Well, instead of measuring the bell basis, you can measure some other basis, and you still get a lot of defects. So the only thing you have the freedom to do at the moment is you have the freedom to apply unitaries to the black wires. These are like the only thing that you're sitting on at the end of your circuit. And now the unitaries you choose to apply could depend on the defects, which is to say, it could depend on what these measurements were. In fact, it should. If you got all 0s, you declare success. If you don't get all 0s, your classical computer turns and makes some decision. And so what are you going to do? Well, it's a little bit of whack-a-mole. You have an ability to put some unitary here. Roughly, you could think, oh, I'm going to commute the unitary through that tensor. What that's going to end up with is going to end up some like extra defects running around. You're hoping that you've chosen smartly, so the defect cancels this to the right, but then you're left with a defect to the left, and now you got to go cancel that defect and the defect that started there already. And so as you fix defects to the right, you sort of produce a new list of the one. Well, what you're hoping is there's some group structure here. So the defect you produced and the new defect sort of combine together into some new single defect. And so you can do this. It turns out that if you have this translationally invariant MPS, you have some representation on the physical aid that corresponds to a representation of the group on the dimensionality that corresponds to the physical dimension. You can commute it through and get a representation on the virtual aids. And so you can then pull off what I promised at the beginning. Okay, to actually prove this, you've got to go right down, got to use the Brando-Algidaldi theorem, group theory, and you have to prove that a POVM exists. It allows you to do this, and these things commute in the way that I promised. And all that is very important, but not something that I want to talk about at the moment. Okay, questions about this?
So actually, I think projective representation is what you care, or is it representation? Because for this MPS symmetry pull-out, the projective representation is actually what you can get, right?
But it's got to be, you've got to have an n-dimensional projective unitary representation. It's got to be irreducible.
Yes.
And that's because if you don't do that, you can't end up with a POVM that measures into this group. When you produce the defects, they're not of the right kind. That's sort of the thing. Great, thanks. Other questions? Okay, so there's some slides for experts that I'm going to skip. So what is the story here? Well, at least some of the time, and actually it looks like at least a lot of the time, as far as our numerics can tell, you can offload some of the quantum work as long as you build up enough entanglements. Okay, let me tell you story two, which has the opposite model, which is that like even if you have a circuit that has lots of entanglement, lots of quantum magic, and I'll tell you what quantum magic is in a moment, it seems that there are many, many of those circuits that are classical computers. But before I start story two, is there any questions? All right, let me tell you what quantum magic is. We've all learned that like the thing that quantum computers are good at is they build up entanglement. That's like one of the things that give quantum computers their power. They're not entangled, they have no power in simulation classically. There's another quantity that someone smartly named quantum magic, which wasn't me. And that quantity is essentially deviation from Cliff radius. So we know that if I hand you these 4 gates, you can do universal quantum computation, H, S, C naught, and T gates. If I hand you 3 of those 4 gates, the H, S, and C naught, these are called Clifford gates. You will use only Clifford gates, you have Clifford circuits, and they have no quantum magic and can be simulated classically using something that's been known forever, these stabilizer terms. So this builds up a lot of entanglement, no quantum magic, by definition. And so there's a classical simulation. But fine, all that tells us is that quantum computers, you need both a lot of entanglement and a lot of magic, and then you're good. Okay, so then it is an interesting question. If I start with these gates and I start putting in some T gates, right? How many T gates can I get in there before I run out of steam and can no longer simulate my thing, my quantum circuit or my classical computer? And the word simulate can do a lot of work. So let me tell you what I mean in this context. What I mean is the following. We're going to ask something weak from our quantum circuit. We would just like to be able to compute some expectation value by quantum circuit with respect to some volumes. That's our only thing. And it's going to turn out, although you can't see it in the bottom corner, you can't see anything. It's going to turn out that if you have a Clifford circuit times something simple, that will be sufficient to compute this expectation value. Clifford circuit can use the Pauli observable, gives you another Pauli observable, and then you can evaluate it. Okay, so this is our goal in the next 5 to 10 minutes. How many T gates can you simulate? 0, and you're back to a Clifford circuit. Stabilizer tableaus have been known to do that forever. A very small number of T gates, you can just use the same technique to eat the blow up. But I have a polynomial number of gates that's universal for quantum computing. And we're all really hoping that you can't simulate that classically, because then quantum computers will be useless. And so one can ask, this is a big chasm between log n and poly n, how many T gates can you simulate? And what we're going to show, let me just like out with the answer. If you have n T gates, which is kind of a lot actually, there are many, but not all quantum circuits that you can, you can simulate this. So that's surprising me. Let me just give you like which circuits. I said there are many of them. I could just like give you a beautiful algebraic characterization of them actually. So here's the game. If I have a Clifford circuit and it has a bunch of T gates in it, which is to say I have any circuit, I can go ahead and I can pull the T gates out. I can commute them out. And if I pull them out of the circuit just to the bottom, T gate is alpha I plus beta Z for some alpha and beta. At the bottom, it's alpha I plus beta P, where P is some Pauli string. Might be a long, complicated Pauli string. ZX, I, XXX. So now I have a Clifford circuit depleted of T gates, but I have these like multi-qubit polys. And I can write out at this point a matrix of these polys. Poly 1 is XZ, YY, XZ. Poly 2 is XXZ, YXX, etc. And then I can just turn it into a matrix of ones and zeros. 1, I can see good as I can do like this is just the TF2 matrix, right? I can do linear algebra on it, I can compute its rank, I can compute its null space. To simulate this circuit classically is exponential in the null space of that matrix. And because many 0-1 matrices are essentially full rank or nearly full rank, there are many cases where I could simulate the insufficient. Okay, so that is like a beautiful, in my opinion, algebraic characterization. I get handed a circuit, commute out the T gates and look at this matrix. The matrix tells me what is the cost of simulating. Yes.
Is there a intuition for why you can forget about X or Y? And just because you're not doing the usual F2.
You're asking why X and Y both map to 1?
Yeah.
Yeah, give me 5 minutes and you'll see. But it's essentially because they both turn 0 and Y onto some base. You'll see it in a minute. Okay, so I told you the characterization. Let me tell you the algorithm. So here you go. Someone hands me you get handed a circuit, and it's got a bunch of T gates in it. Circuits happen to have. And what you do is you pull out the first alpha I plus beta some poly. And now you look at that poly and you're like, oh, here's an X or a Y, but in this case, an X that's hitting 0. And so when an X hits a 0, an X is just a non-gate, turns a 0 into a 1. Okay? So I have alpha 0, 0, 0, 0, 0, right? Identity didn't do anything to that state, plus beta times this thing. Okay? So on the beta branch, I have a 1 here. Instead of an X, I've just changed it to the identity because I already like dealt with the X. And then I have some other things. I have Y and X and Z. And when these things hit my circuit, hit my state, it's just going to make a mess of my state. So what we like is we like these things to go away. And how are we going to do that? Well, we have a 1 here. And so we're going to use sort of an age-old technique of multiplying by identity, right? This is all physicists do. We're going to insert DD dagger, which is nothing, into our circuit. But D is going to have this property. It's going to, on the wire that I've turned that 0 into the 1, it's going to have a bunch of control Y, control X, control Z. So on this branch where everybody is 0, it does nothing, the alpha branch. But on the beta branch, any place that there is a poly that is causing us trouble, we're going to make it go away. So this now becomes Y squared, because this qubit is 1. So that control Y happens. This is going to be X squared, and this is going to be Z squared. Those are all identical. And so where are we now? Well, at least for this part of the circuit, what has happened is this qubit has been used. It's been changed because we have alpha 0 on that qubit plus beta 1 on that. But we saved all the other qubits. We used that 1 that existed here to have control polys that turned off the rest of the circuits. Felix, this is the answer to your question. Y on 0 is the same thing. You get 1 up to a phase, and so you can also use other. Okay, so good. And now I have a state that is only like minorly affected. In some sense, I've like burnt this qubit. It's been consumed. I'm not going to get to use it for the rest of my algorithm, but I at least got to use it once. And now what am I left with? Well, I still have D dagger running around. But D dagger is a bunch of control polys. Control polys are Cliffords. So I'm back to having a Clifford with some T gates in it, 1 less than I had before. And the initial state, it looks a lot like I had before, but I've consumed one of the qubits. And now I can just play this game again. Okay, let me pull the next T gate out. It has some poly. Oh, there's a Y on 0 here. That produces a 1 qubit. I can write, what was the only thing that I needed? I needed that there was an X or Y sitting on some 0. So they're here, there's a Y on that 0. Let me pick that 1 and consume that qubit. Yes.
So what do you mean by burning the initial qubit?
Well, once I've used this, once I've applied this X to this qubit, what I'm left with is alpha 0 plus beta 1. So now that is a qubit that is in some magic state, alpha 0 plus beta 1. And just by burn, I'm just thinking of these zeros as a resource. Right? A 0 that has an X or Y on it, I can use it. If it's alpha 0 plus beta 1, I can't use it. Sure. And so like just burn just means like I consume. So like I'm not thinking about it anymore. It's like hang down. Sure. That's all. Okay, so now there's a Y on the 0. I'll do the same thing. I'll turn it into the 1, put the control polys there. At the end of the day, I'll have a new Clifford circuit where both of these are magic qubits, but everybody else is still assumed. And then I can do it again. Good. So in this case, I chose X on 0, and I'm in good shape. And now I pull the next T gate out, and I'm in trouble. Why am I in trouble? Well, I have Z on 0 and I on 0 and I on 0, but then I have no way to actually go ahead and turn one of them into a 1, so I can use it for my control. So what do I do now? Well, I'm in trouble, but actually there's a very nice property of this. This is alpha I plus beta this. And this here is going to make a mess of these 3 consumed qubits. But it's not going to touch the zeros that are sitting. So it's going to entangle these 3 qubits that are on fire if I just like absorb it into my state. And I have an entangled fire. But these zeros are still useful untouched resources that I can use in the future. So this is kind of a failure on that one, string. But okay, and then I can pull out the next 2 T gates and maybe they consume other zeros. So what do we end up with? Well, at each of these steps, our Clifford grew. So it didn't grow my slide, but it grew because at each of these steps we had a T dagger that we had to absorb into a bigger Clifford. But that's okay. We're okay having a Clifford in some state. We said at the beginning of this story that the Clifford times some state, we can compute all the expectation values too efficiently, as long as this state isn't too complicated. Well, what is the size of this state? Well, what happens every time I fail? Well, my state gets more complicated. How much more complicated? Well, it essentially at most doubles the Bonham excitation. I essentially have a state whose size is at most exponential in the number of times that I fail. Okay. And it turns out that the failures is equal to the number of Pauli strings in the null space. It's not obvious why this is, and I'm going to not tell you. But I have 3 slides that tell you, so if you want to know. Okay, so now I'm done. What is the moral of this story? Well, classical computers can simulate a lot of quantum circuits, a lot of entanglement, and a lot of magic. What is the conclusion? So let me actually start with this part of the conclusion. This is sort of a statement about fundamentals. We, or at least I, no longer understand intuitively like where the power of quantum computing is coming. Because here, this is like a bunch of circuits, like a lot of entanglement, a lot of magic. These are the things that I thought made quantum computers powerful. And yet, a bunch of them, although not all of them, we can go ahead and see. So this breaks some intuition. In addition, what we've seen is the goal. Well, the goal of quantum computers is to sort of exponentially surpass some problems that classical computers can't do. To get there, we have to develop a lot of components, and it looks like many of them will involve sort of quantum computing working in concert with classical computers. So I showed you one example where if you do that, you actually get sort of major wins. And so the circuits out that we need to build using measurement as adaptive feedback. But of course, there are lots of other examples of these: quantum error correction, hybrid quantum classical algorithms, etc. And so this is sort of the fundamental statement. And so really mapping the boundary between classical and quantum computing is sort of both a practical thing, kind of helps us in engineering, get over the way to building useful quantum computers or programming useful quantum computers, and also sort of deeply fundamental. I think that's what I wanted to say. Questions?
Actually, you pulled out all the T to the initial state.
Yeah.
But like, how does it make the classical simulation easy? Now you already completed the initial state, so.
Because all of these T gates got absorbed into this state.
Yes.
The size of this state is exponential in the number of T gates where I was not able to consume.
Yeah, but like if you have n T gates, then
They're n.
exponential is n.
No, there are n qubits around. Each T gate that I absorb doesn't increase the complexity of that state at all. It leaves the entanglement identical. See, in this case, where I've absorbed this T gate, this is what I left with. This is now a magic state here. This is still a product state. This is not more complicated at all.
Yeah, but it doesn't matter, right? Because if you evolve it using the Clifford evolution, the thing's gonna happen.
Good. So once I have a state that is Clifford terms of product state, it is trivial to evaluate the expectation values of a Pauli respect.
For Pauli's, yes, I agree.
Right. So my only goal was to compute the expectation value of whatever state I ended up with respect to some point, xx. That is the sense in which I can see. So you're right. If I wanted to do something fancier on this state, I wanted to sample from it, that is a different story. Right? So maybe you say, oh, really the power from computing is coming from Sam. But lots of things that we might want to do is just compute some expectation of. What is the energy of this speed? What is that? So this is sort of what I said about simulating up front. Yeah.
Is it best to remove all the T gates or just until you have like log n T gates? So maybe you have some flexibility to choose which T gates you absorb.
Yeah, I mean, you might as well absorb any of the ones that you can absorb because it costs you nothing. But then in some sense, you're right, you can now afford essentially log n T gates that you can. Because log n T gates that you can absorb blows it up to a polynomial bond dimension and you can afford polynomials. Yes.
Is it possible to somehow transform this simulation algorithm into better classical code for computing things that you didn't know how to?
Not in any deep way that I know. I mean, we can compute some properties of some quantum circuits that we just know they can compute. And I'm sure we'll see.
Yeah.
You might ask, like, is there so many body? Okay, that's not true. I mean, there are people that have done sort of similar work using slightly different algorithms, looking at like measurement into space transitions and circuits. So there's some like physics things that we know how to do a bit better because of this. But I don't know, like generically, a lot of things. Most of the circuits you care about have more than integers.
Oh, I see. So what you're saying is that like up to n T gates, it's kind of easy to keep record of the initial state, so that's fine.
Up to n T gates, the initial state that you're doing is simple.
Yeah.
In many cases, so that's fine. If you have more than n T gates, well, then the null space is like n plus whatever you want. And so if you have two n T gates, your null space is n, so exponential n, so you're in trouble. Like it's not order n, it's like literally n is sort of like the special like. Maybe other questions? Thanks.
So if it's like find an n, if it's like make it initial state to be a highly entangled.
If your initial state is not all zeros, none of this works.
Yeah, I want to say initial state all zero.